You know, we trust software with our lives every single day. And most of the time, we don't even think about it. But what about the code that's flying our planes, or running our power grids, or monitoring a patient's heartbeat? That's not your average app. This is software that absolutely, positively cannot fail. Today, we're going to pull back the curtain on the hidden world of dependability engineering.
So let me ask you, what's really keeping a jumbo jet cruising at 35,000 feet? Or keeping a city's lights on during a blizzard? Now, sure, you've got the massive engines, the physical hardware, and of course that's essential. But that's only half the story. The other half is completely invisible.
The silent partner in all of these critical systems is the software. We're talking millions of lines of code, meticulously engineered and tested to perform perfectly when the stakes couldn't be higher. This is software that's built for a level of trust most of us, thankfully, never have to worry about. So how in the world do engineers pull this off? Well, here's what we're going to cover. First, we'll look at the incredible stakes they're up against. Then, we'll unpack the 3 core principles they use to build trust. After that, we'll see how they use redundancy and diversity to create some truly bulletproof blueprints. And finally, we'll zoom all the way down to a single programmer to see how it all starts with just one line of code. All right, so first things first. Why does this field even exist? It's simple, really. For some systems, the cost of failure isn't measured in dollars, it's measured in lives. We're talking about the flight control systems on an airplane, the software running inside a pacemaker, or the systems controlling a nuclear reactor. In these areas, dependability is completely non-negotiable. These systems are so critical they're often regulated, which means they need a stamp of approval from an outside authority before they can ever go into service.
And you know, there's also a huge economic reason to get this right the first time. Finding a bug on a developer's computer, that's one thing. But finding that same bug after the software has been installed in, say, 1 million cars or deployed to a national power grid, the cost to recall and fix it just explodes. It becomes a logistical and financial nightmare. This is exactly why the entire philosophy is built around preventing errors from ever happening in the first place.
Okay, so how do you actually build software that you can bet lives on? It's not magic. It turns out engineers rely on this really powerful 3-part strategy to make it happen. It all comes down to these 3 pillars: fault avoidance, fault detection, and fault tolerance. Think of it like a series of defensive walls. First, you try to prevent mistakes entirely. Then, you hunt down any that might have slipped past that first wall. And finally, you design the entire system to actually withstand the impact of any bug that still somehow makes it through.
The first pillar, fault avoidance, is all about the process. The goal here isn't to rely on one genius coder. Instead, you create a system of development that's so rigorous and well-defined that human error has almost no room to creep in. It's all about getting it right before a single line of code is even considered final.
But hey, no process is perfect, right? And that brings us to fault detection. This is the search and destroy phase. Here, engineers basically become detectives. They use every tool in their arsenal, code reviews, design inspections, massive automated testing suites, to hunt down and eliminate any bugs before the system gets anywhere near the real world.
And this leads to maybe the most critical mindset shift of all: fault tolerance. Engineers have to start with the assumption that, despite all their best efforts, a flaw might still exist in the final product. So, what do? They design the system to survive its own failures. This is the real art form, making sure that one little component failing doesn't bring the whole system crashing down.
So how do you actually achieve that fault tolerance? Well, the 2 most fundamental tools in the engineer's toolkit are redundancy and diversity. Redundancy is pretty easy to grasp. You just have backup copies. Think of it like having a spare tire in your car. If you get a flat, an identical replacement is ready to go. Simple. Diversity, though, is a bit more clever. It's about solving the same problem in different ways. This is like having a spare tire and a can of Fix-A-Flat. If there's some kind of fundamental design flaw in all your tires that makes them all vulnerable, well, that Fix-A-Flat might still save you.
And you see these concepts out in the wild all the time. That e-commerce site that has backup servers ready to take over if the main one crashes, that's pure redundancy. But what about a company that runs its services on both Windows and Linux servers? That's diversity. An attack that targets a specific Windows bug won't even touch their Linux machines, which keeps the whole service resilient. Okay, so armed with these 2 powerful tools, redundancy and diversity, engineers can now start designing specific blueprints for building these nearly indestructible systems.
One really common pattern is called the protection system.
You can think of this as a separate, much simpler, and totally independent watchdog. Its only job is to monitor the main control system and the environment. If it detects a dangerous condition, like a reactor overheating, it has one job and one job only. Take emergency action, like triggering a shutdown, completely bypassing the main system.
Another really powerful blueprint is the self-monitoring architecture. This is where it gets cool. You have multiple channels, we're talking separate hardware and software, all performing the exact same calculation at the same time. The system is constantly comparing their answers. If those outputs ever disagree, even for a split second, the system knows something is wrong and immediately flags a failure. This whole process is often called system voting.
And look, this isn't just some theory from a textbook. This is the exact approach at the very core of the flight control systems for the entire Airbus fleet of aircraft. That's right, when you're flying on an Airbus, this constant voting among computers is what's keeping the plane safe and stable. And Airbus takes this idea to a whole other level. It's actually mind-blowing. They use 5 separate computers. The primary and secondary systems use processors from different manufacturers just to make sure a microscopic flaw in one chip's design won't affect the backup. The software is written by entirely different teams, sometimes even in different programming languages. They are doing everything humanly possible to prevent what's called a common mode failure, that one tiny, identical mistake that could bring down multiple, identical systems all at once.
All right, now let's zoom in. Let's go from that 30,000-foot view of system architecture right down to the individual programmer. Because at the end of the day, all of this starts with the discipline and habits of writing dependable code.
The number one golden rule is to never, ever trust your inputs. A program has to protect itself from any unexpected, messed up, or even malicious data coming from the outside world. This means checking if data is in the right range, the right size, and the right format before you ever try to do anything with it.
And this is so important, because an incredible number of system failures and security breaches all boil down to this one simple mistake. A program being fed data it just wasn't built to handle. That's why validating every single input is basically the first rule of defensive programming.
And finally, dependable programming means being extremely careful with certain coding features that are powerful, but also kind of risky. For example, using pointers can be like handling a live wire. One tiny mistake can corrupt a completely unrelated part of the system's memory. Or trying to use floating point numbers for money. Because of how computers do math, 0.1 plus 0.2 might not equal 0.3 exactly, which is, a total disaster in a financial system. The goal is to avoid these kinds of subtle, hard-to-find bugs that can have massive consequences.
So we've seen these incredible layers of defense, from huge architectural designs all the way down to a single line of code, but it all comes back to one fundamental truth. Perfect, 100% bug-free software is impossible. And that leaves us with the ultimate challenge. It's not just about building robust systems. It's about deciding when a system is robust enough to bet our lives on.